In this lesson, you're going to learn how to solve quantitative problems that involve numbers and involve gases changing pressures, temperatures, volumes, and numbers of particles. So we're actually going to do some math now with the relationships we've learned in the lab. In these problems, first step is to fill out this table here with what we know and figure out what we're trying to figure out. So the table, the first two rows are going to be filled with numbers that we get from the problem. Initial is our starting conditions. What is the gas conditions at the beginning, and final or ending conditions. As I read through my problem, I'm going to put each number I encounter somewhere in this table. So a balloon with a volume of 2 liters. 2 liters, I need to put a 2 under volume. Is filled with a gas at 3 atmospheres. The 3 atmospheres is happening at the same time as the 2 liters. So I'm going to put that 3.0 atmospheres in the box for pressure. It says the pressure is changed. Okay, so it's gone from the initial conditions to the final conditions. It's changed to a half an atmosphere, 0.50 atmospheres. Without a change in temperature. Alright, well that means we don't need the temperature column in this problem. And it says, what is the new volume of the balloon? So this is the block that I don't know. I'm going to assume, since it didn't mention anything about number of particles, that that is also kept constant in this problem. I'm going to use the third row effect to decide what effect the pressure would have on the volume. In this problem, the pressure went down. We learned in the lab this past week that when pressure goes down, volume goes the opposite direction, so it would go up. It is an inverse relationship. Now that we've decided we are expecting our final volume to be bigger than 2 liters, we're going to figure out how much bigger it is by using some proportions. We're going to start our little problem by writing the initial condition of the variable where we only know initial condition, so in this case volume. Then we're going to set up a fraction to multiply by that with pressure on top and bottom. Now I've got to decide, do I put the 3 on the top in the numerator or on the bottom in the denominator? Where do I put the half? Well, I know that I've got to make this 2 liters get bigger. So I need a number here that is greater than 1 in order to accomplish that. 3 divided by 1/2 is going to be greater than 1, so I'm going to put 3.0 atmospheres on the top. I'm going to put 1/2 atmosphere on the bottom. Then I'm just going to do the math. First, before I do that, I want to confirm I've got atmospheres on the top and the bottom so they cancel each other out, and I'm left with units of liters, which is the units that I want my answer to have, so that is good. Now I'm going to do the calculation. 2 times 3 divided by 1/2 equals 12 liters. You also always want to double check significant figures. We've got 2 significant figures here, 2 significant figures here, 2 significant figures here. So my answer should have 2 significant figures, and it does, so that is a very good thing. Sandy check here, I expected volume to go up. 12 is higher than 2, so that matches my expectations. The last step is to check our work, or to confirm our work by drawing pictures. If our initial volume is 2 liters, that's a smaller box, and our final volume is 12 liters, a much bigger box. The number of particles stayed the same. I'm going to represent that, so I've got maybe 4 particles in this box. I have 4 particles in this box. The temperature stayed the same. So if these all have 1 whoosh, these should all have 1 whoosh. And you can see that my pictures show that the pressure got lower as the volume got higher. We have one more example to go through before you're going to try some of these on your own in class. We have a 600 milliliter sample of nitrogen heated from 27 degrees Celsius to 77 degrees Celsius at constant pressure. So let's put these numbers in. 600 milliliters is a volume, so I'm going to put that right here. I don't know the final volume, so I'm going to put a question mark there. Heated from 27 degrees Celsius to 77 degrees Celsius at a constant pressure. So I'm going to put cross out pressure, we don't need that, and it doesn't mention particles, so I'm going to assume they're constant as well. One thing about the temperatures is they have to be, as we learned in the lab, in this new scale called Kelvin. So I've got to convert 27 degrees Celsius and 77 degrees Celsius to Kelvin by adding 273 to each of those numbers. Alright, so we've converted the Kelvin or the Celsius temperatures into Kelvin so that we're using a scale where 0 pressure is the point where all movement stops, 0 Kelvin. In the problem it says it's heated from 27 degrees to 77. So 27 degrees Celsius or 300 Kelvin is the initial temperature. And 350 Kelvin is our final temperature. Again, we look at the relationships next. Our temperature went up, and as a result, we're expecting our volume to also go up. We found that was a direct relationship. So again, I start with the number that I know the least about, the 600 milliliters. I'm going to multiply, set up a little fraction here. I want my volume to get bigger, so I need to set up a fraction that is greater than 1. That means this time I want to put 350 Kelvin on the top and 300 Kelvin on the bottom. Multiply that out. I did the multiplication and I got 700 milliliters. Next, check significant figures. I've got 1 significant figure here, 2 here, 2 here, so my answer should have 1. It currently does have 1, so that's correct. Finally, sanity check. I expected my volume to go up. My volume did go up, so this is exactly what I was expecting. Finally, we're going to draw a picture to represent the situation, initial and final. We've got a box here that's 600 milliliters, and it would be good on your homework to maybe label your pictures. So this is 600 milliliters, and this one is 700 milliliters. And we said maybe we have the number of particles are the same, so let's pick 5 particles this time. The pressure is the same, so if I have 1 swishy here and 1 collision here, I need to have 1 swishy and 1 collision in this problem as well. And I put 2 swishes to show that those particles are moving faster in the bigger volume. Those are my 2 examples, and you're ready to start some problems on your own.